Good morning, everybody. Hopefully you guys are doing well this morning. If we can start with some green check marks, please, and then we will get into some of this radiation stuff. I have not necessarily a review. I just want to kind of look at a few different concepts and then answer any questions you guys have, and then we'll be done. Radiation, Unit 7, which leaves us 8 and 9 left, and hopefully we'll finish those off over the next week and a half or so, maybe 2 weeks. Give us about a week and a bit for review. So that's where we're at. We're a lot closer to the end than it seems. I know we're still in May, but it goes fast. So if you guys have specific questions, you can throw them in a chat. I just wanted to start with a little, I don't know what we're going to call it, a little demonstration, I guess. So this is one of these little interactive things. 2 more costs and 2 more units. And it does a really good job of describing how nuclear fission happens. I don't have one for fusion, but we'll do this one anyway. So this is kind of what happens in nuclear power plants or nuclear bombs. And I did some reading and I only found, we've only discovered one instance on Earth where nuclear fission occurred kind of spontaneously, and it was in Africa somewhere where there was a really high concentration of uranium atoms, and it just started to kind of get really hot. Didn't blow up or anything. So there's 2 isotopes of uranium. Well, there's more than 2, but mainly we're going to talk about uranium-235 because uranium-235 is very unstable when it gets hit with a neutron. So when you have a nuclear power plant, or if you have a nuclear weapon, you want as much uranium-235 as you can get in it. The more the better, because when uranium-235 undergoes fission, it releases 3 additional neutrons, and that's what continues the chain reaction. That's why we can harness energy from it. So you can see what happens is this uranium-235 has all these protons and neutrons in the nucleus. It's fairly stable at this point. Now this little neutron blaster is going to fire another neutron into the nucleus, and it's going to get absorbed. So what happens is when that extra neutron gets absorbed into the nucleus, it turns into uranium-236, and then eventually it breaks down because it has too much energy. So that's what this is showing on the bottom. This little graph is showing the amount of energy it has. So we'll just do that one more time. So uranium-235 gets a neutron, changes to uranium-236, becomes unstable, and then it breaks apart into its daughter products, essentially. So that is just one. If we have a whole lot, so let's add 100 atoms of uranium-235, and I take my super-duper neutron blaster and I aim it at just one nucleus, and it breaks apart. The 3 neutrons that are produced go and hit other atoms, and they all break apart. And that's exactly how a chain reaction works. So that is essentially what's happening in a nuclear reactor, in a nuclear weapon. Once you get what's called a critical mass, which is the actual mass of uranium needed for spontaneous fission to occur, that's what they use in kind of bombs and things like that. Generally speaking, in nuclear power plants, you don't want to have a critical mass because your power plant can turn into a bomb very quickly if things happen. But sometimes they have enough uranium on hand to do stuff like that. So you can see everything just kind of breaks apart. New neutrons are created. They find new atoms, and they all eventually break up. Now, the problem with uranium-235 is it's not the most abundant isotope. Most of uranium is the uranium-238. So let's get rid of the U-235. Let's add some U-238. So the majority of uranium we find in nature is the uranium-238. So I'm going to aim at just this one nucleus here. And you'll see when the neutron hits it, it's kind of anticlimactic, but uranium-238, when it absorbs a neutron, it changes into uranium-239, and that's a stable isotope. So when we have a sample of uranium, we want to try to get as much uranium-235 out of it as possible because that's the one that undergoes fission, whereas uranium-238 is just going to absorb the neutron and nothing's going to happen. So no matter how many of these atoms I hit, I'm going to get no chain reaction happening. It's just going to change into uranium-239. Let's grab another one so you can see it here. I'll skip through that one. So boom, changes to uranium-239. No fission occurs. It's stable. So yeah, essentially that's how nuclear fission occurs. Now this is kind of, well, this is supposed to simulate a nuclear reactor. So in each one of these sort of columns, I guess, you have a bunch of uranium-235 atoms. And what I can do is I can fire a neutron in here, and you'll see that it starts to fission right over here. And we're kind of hoping for a chain reaction to happen, but you know, sometimes it doesn't happen. I also have these things called control rods, and if you remember from last day, control rods are usually made out of carbon. So just like graphite that you'd have in like pencil, special graphite, but graphite, just carbon. And carbon's really good absorbing extra neutrons. So if I pull the control rods all the way out and I fire a neutron, you can start to see fission happening, and it's starting to change color a little bit because it's getting hotter and hotter and hotter and hotter and hotter. And this is essentially what happens when a power plant melts down, is that all this fission is happening and you're not able to control the speed at which it happens, and your reactor core gets too hot and it literally melts the container that it's in. The liquid that it sits in will boil. The actual physical container, even though it's made of really special types of metal and whatnot, they'll start to melt because it's just so hot, so much heat is being produced. So I'll just reset this again and see if we can, there we go. So we get the fission occurring. What I can do is I can put in the control rods, and you can see it slows down the reaction a little bit. And then if I pull out the control rods, it continues to go, and then I can slow it down a little bit by putting them in. And I can completely stop the reaction if I leave the control rods in, because all those extra neutrons just get absorbed by the control rods. So that is how a nuclear reactor works. There's actually a picture of a reactor core here, which we should probably look at while we're here. And this is the Penn State University has its own nuclear reactor, and this is what it looks like. And it kind of glows because of all the nuclear reactions that are occurring there. But this, I don't know how exactly this reactor works, but probably this apparatus, the black stuff, kind of lowers in as control rods. This bluish stuff would be some sort of liquid, probably water, but heavy water. And heavy water just has, it's H2O, but the isotope of hydrogen, the isotope isn't just regular hydrogen with one proton. It's usually deuterium, which has 2 neutrons, so 1 proton, 2 neutrons. And that is good because it slows down the neutrons, and if the neutrons get going too fast, they won't get absorbed. So that's generally how a nuclear reactor works. So those are the ideas. Chain reactions, you have neutron being absorbed, things break apart, creates 3 more neutrons, and the reaction just occurs very, very quickly. Anybody have any questions about nuclear reactors, chain reactions, fission, and anything to do with those 3 ideas? Let's see what happens here. Put a bunch of uranium in a containment vessel. For sure, Costin, I'll get to that in a second. There you go. So that is how things break down radioactively. I always like to show this video because students generally generally don't have a strong understanding of nuclear weapons and detonations and things like that. So usually at this point I ask, how many nuclear bombs have been detonated on Earth? What do we think? Just throw a number in the chat, just guess how many nuclear bombs have been detonated on Earth since 1945, when the first one was detonated. We got 120, 2,000, going big, Kyla, I like it. 10. Yeah, so basically we'll watch this video. The frame rate will be kind of goofy because we'll watch it here. I'll make sure the sound's off so we don't run into any trouble. This shows every known detonation. We're pretty sure we know of all the detonations. When a nuclear weapon gets detonated, remember when we talked about seismic stations measuring the vibrations of the Earth? So a nuclear bomb is, when it goes off, is really similar to, or any big explosion for that matter, is very similar to an earthquake. It creates waves that travel through the Earth, and we have very accurate seismic stations all over the place, so when a bomb goes off, we can pinpoint exactly where the bomb was detonated. So it's not really a secret where the bombs go off. We always know when somebody else tests a bomb and things like that. So in my lifetime, when I was born in the 80s, they were still testing weapons above ground on our planet. Usually they'd bury them so the radiation wouldn't go into the atmosphere. But now we have computers that are powerful enough to simulate a nuclear detonation. So they don't test bombs at all anymore. They can put all of the information into a supercomputer, press run, and then they can kind of simulate what's going to happen when a bomb gets detonated. With the exception of North Korea. North Korea likes to test their weapons still. I'm not sure if they don't have the supercomputers or what the story is. I think it might just be because they like other people to know that they have nuclear weapons. But I think it was within the last year they've detonated 2 nuclear weapons just to test them. And yeah, pretty scary stuff. So I'll just go through this. The kind of periods we'll see is the beginning is the first weapon that was ever tested was Project Trinity, which was detonated in New Mexico. That was the first one. Not too long later, they detonated one in Hiroshima, and a few days later in Nagasaki, Japan. Ended the Second World War. Then you get this kind of lull where it's just the United States that has the weapon, and then eventually some other countries will come on the scene and develop a weapon, leading into the Cold War, which was an arms race between the United States and Russia. Lots of weapons testing, lots of different bombs that they were testing, both hydrogen bombs and fission bombs. I should mention that a hydrogen bomb is a fusion bomb, and it's the only way we can get hydrogen to fuse together is to ignite it essentially with a fission bomb, because that's how we can get really high temperatures. So when you hear of like an H bomb, a hydrogen bomb, that's a fusion bomb, way bigger than a fission bomb. But the only way we can get a fusion bomb to work is if we have a fission bomb to go off first to get it hot enough, and then the hydrogen and different isotopes of hydrogen will fuse together. So we'll full screen it. There's lots of videos like this on YouTube now. This is the first one I've saw. So in the top right corner you can see, maybe you can't see, it's cut off on my screen. It gives you the date, 7th month, 1945, and gives you the first bomb detonated in New Mexico. So there's the first one that went off. Each time a bomb gets detonated, you get a little dot. And the counter up on the top and then eventually on the bottom indicates how many bombs have been detonated. And then the bottom right corner has a running total. Can you guys see the bottom right corner? There's a 1 there now. It's cut off on my screen, but I was wondering if you guys could see it. So there's the second bomb ever detonated in Hiroshima, Japan, and then a few days later in Nagasaki. So that's 3 bombs in about a month. The ones that they detonated in Japan were fairly crude. One was a uranium bomb and one was a plutonium bomb. So then you can see the timer in the top corner just kind of ticks away. We're at 3 bombs. So this is 1946 now. Nothing really happening. And you see some bombs being detonated in the South Pacific. These are some islands here in the South Pacific the United States owned. Bikini Atoll was one, and some other ones. And they used the location in the South Pacific because it was very isolated, far away from everyone. They weren't really sure what the radiation was doing to people, things like that. So 1948, about 2 years after the end of the World War, 1949, the United States detonated 8 bombs in total. And then in 1949, Soviet Union at the time developed technology to detonate a bomb. So you see the little flash from the Soviet Union. And time kind of chugs along. As 1950, we've got 9 bombs detonated in total at this point. So 1951, you'll see a bunch start to get detonated. So the United States is up to about 17, 22, 23, 24. Lost video. Do you still have video, Mr. Ross?
Nope, I lost you.
You lost me. All right. Let's see if you can get me back. No go? Sorry, guys. We're just... well, there we go. Can we continue for there, do you think?
Yeah.
Okay. Did it just not like the full screen? Seems to be fine. So where were we? We were in 1950 something, 51. So we're up to 20 bombs in total, and you see the number starts to kind of climb really fast for a while. Here we are in 1952. The United Kingdom starts to test bombs. You'll notice the United Kingdom has a different color of bomb. Each country is represented with a different color, but United Kingdom's so small, you couldn't detonate bombs in the UK because there's so many people around. So United Kingdom tests their bombs in either United States, in Australia, or in the South Pacific. They test all their weapons there. So we're at 120-ish now, 1956. Probably getting close to when your parents were born. I would imagine your parents were probably born in like the 60s and 70s. Why do they need to do so many bombs? You ain't seen nothing yet, Costin. We're just getting warmed up. It's only 1958. Cold War just starting. There you go. United States is going to town now. So 1959, getting close to 1960. Here comes France. France develops their first weapon 1960. You see France's green dots, they test their weapons in northern Africa, which had some French colonies. These are all just testing. The only 2 bombs that have ever been dropped during wars were in 1945 to end the Second World War. So now we get in kind of the height of the Cold War, and see both the United States and the Soviet Union are feverishly testing weapons. France does a few. Yeah, the actual cost of one weapon is probably in the high millions. Here's China in 1964. I just imagine the amount of money that would go into refining the uranium, the actual technology, the amount of people that it would take to build a bomb. Like, I don't even know, I can't even fathom how much money was spent on detonating all these bombs. notice the United Kingdom gets to 26 and they're like, okay, we got things under control, we know how to do it. And everyone else is just like, we need to test more bombs. And they're like, no guys, 26 is probably good. We can just leave it at 26. I'm not sure, Eric. I don't know a lot of the history of why they detonated so many. It would have been probably different types. They would have been testing structures. So it wouldn't always been just about the bomb. They would have wanted to test, you know, the ability to survive a detonation. They would have wanted to test the effects of the fallout, the radiation that was created as a result. There would have been lots of things they would have been interested in testing, not necessarily just how big of a bomb they could blow up. Although they blew up some really big bombs. Jesse, they always drop the bombs in the same spot, or I say drop. Some would come from a plane, some would have been launched out of cannons, some would have just been stationary and detonated. So they had specific locations where they would continue to test bombs again and again and again. I don't know if they figured it out. I mean, the United States and the United Kingdom have always been allies, so the UK probably was like, you guys got it figured out, we'll just be happy with our few little bombs. So there's India, 1974. They test a few. Meanwhile, the United States and Soviet Union continue their little spat. I'll just fast forward a little bit. We get up to nothing really happens other than flashes of light. You get Pakistan comes on the scene here pretty soon. There's Pakistan with their 2 bombs. So this is 1998. So this ends at 98. And about that time is when, no, Canada never detonated any nuclear weapons. We're a non-nuclear nation. So that gives you a bit of an idea. And Kyla, 2000, that was a tremendous guess, or you knew. So there you go. It gives you a bit of a running total of each of the bombs, or countries' bombs. If we go right to the end of the video, it shows each country, and it shows where all their bombs were detonated. So this is France's 210 bombs. And it gives you kind of like a heat map. The white circles gives you, it's not that's how much radiation was created or anything, it just gives you an idea of where the nuclear bombs were detonated and frequency. So you can see the UK has their bombs in Australia and United States and South Pacific. Here's the Soviet Union's 715 nuclear detonations. It's like a fireworks show. Pretty crazy, all over the place. And then United States detonated just over 1,000 bombs. So lots in southern United States, South Pacific. There you go, there's your grand total. About 2,053 weapons detonated. Oops. In about 60, that went to 1998, so about 60 or so years. This will continue now, and like I say, most bombs are detonated just in computer simulations, with the exception of North Korea, who likes to blow theirs up on land still. But generally speaking, underground. And that's kind of crazy to think, I know. I find it crazy to think about it. And I think you should too, because it's kind of scary. Another thing I want to talk about is we talked a little bit about radiation and how our bodies receive radiation. And we watched a couple of videos. This was a week and a half ago or so. And this is a little bit hard to read. Let's make it a bit bigger. There we go. So this is your sort of dose of radiation that you'll receive if you encounter these objects. So I just had a banana for breakfast. So we measure everything in microsieverts. And eating a banana is 0.1 microsieverts. Adds to your radiation. You guys don't usually have CRT monitors. Those are like the really big tube TVs. They're called cathode ray tube TVs. We used to have them, not so much anymore. Using one for a year would be 1. A dental x-ray, you probably get 1 a year. You're looking at 5. If you were living near Fukushima, which is where the reactor melted down, you'd get up to about 3.5, and that's for a day. The 3 Mile Island nuclear meltdown would give you about 1,000. And those were for people who lived near the meltdown. So that was 1,000. Keep that 1,000 number in mind because we're going to compare the 3 Mile Island nuclear meltdown to the one in Chernobyl. So the one, 3 Mile Island, was about 1,000. Anybody have like chest x-rays before? You're looking at about 100. And then this number down at the bottom here, this 2,000, is your the amount you'd be exposed to, the typical person in a year would be exposed to about 2,000. If you get a mammogram, you're up to 3,000, 1 mammogram. A CT scan's 10,000, and my mom, when she was undergoing cancer treatment, she'd get about 2 of those a year. So that'd be 20,000 microsieverts a year just for CT scans. Comparing that to a smoker, and Connor, you probably just had a lot recently, yeah. Smoker, if you smoke 1.5 packs a day, it's 36,000. So literally the most radiation you could receive in a year, sort of naturally, well, not naturally I should say, but by doing something, would be smoking a pack of cigarettes a day because of all the radioactive stuff that's in there. In spending an hour near Chernobyl in 2010, remember the reactor melted down about 30 years prior, it was 6,000. If you work for the US government, you can get a maximum dose of 50,000. Once you get up to 50,000, you can't work anymore for that year. Life-saving workers can get up to 250,000. And then if you were at Fukushima when it melted down, you get 400,000. So remember, the 3 Mile Island was about 5,000. Fukushima's 400,000. And then we're going to look at Chernobyl and why Chernobyl is such a scary one. If you get up to 100,000, your increased likelihood of developing cancer goes up. And 500,000, you're about a 1 in 250 chance. So we get up to 1 million. You can get temporary radiation sickness, and that would have been per hour at Fukushima, would have given you, just outside of the number 2 reactor, would have given you a dose of 1 million. And that would make you sick. Your likelihood of getting cancer goes to 125. 2 million, severe radiation poisoning causes you to get really sick, nausea, vomiting. 3 million, that's bad news bears. Your cancer risk goes to 1 in 30. So that's not good news. 4 million, that's about severe. So if you don't get treatment right away, you'd likely die at 4 million. 5 million, this kills 50% of people within the month. 6 million, the people who were at the Chernobyl power plant who went in to save, after the explosion happened, the first responders would have received a dose of 6 million. They all died. They didn't really know that it was that radioactive, and they went in to help, and basically all the first responders died. And then we go to the bottom. 8 million is a fatal dose, even with treatment. And then if you were standing next to the Chernobyl reactor as it was melting down, you would have got a dose of 50 million. So that's 10 minutes next to the reactor during the meltdown. So just to contrast that with the Fukushima one, this is 50 million. The Fukushima one, 2011, would have been about 1 million. And then the 3 Mile Island one just released, the 5,000 or 6,000, sorry. Where's 3 Mile Island? Lost it. Oh, 1,000 for the 3 Mile Island, people who live near it. So that gives you a general idea. The most exposure you'll probably get would be from things like X-rays, or if you fly in a plane from the higher you get, the less atmosphere there is to protect you. So a flight from New York to LA gives you a dose about 40. Yeah, it gives you an idea of, comparatively speaking, what's going on in terms of radiation. So pretty scary stuff, especially the Chernobyl power plant meltdown. That was bad news. When, Costin? When would you like to go through your question, Costin? Costin must see this question now. Nuclear reaction 4 and 2. All right. So this is a learning guide. For sure, Eric, do 13 as well. 4 and 3. What are you changing your questions, Costin? Confusing me? 4, 3, and 2. You just want me to do all of them? And 5. Okay. We'll do as many of these as we can. So Canadian nuclear reactors are called CANDU reactors. That was in the notes. What are two things that are always produced when a fission reaction occurs? The big ones are energy. That's why we make bombs out of fission and nuclear power plants. And the other one is neutrons. And those neutrons are important because those are what continues the reaction. Without the extra neutrons being produced, we wouldn't be sitting here talking about nuclear fission because nothing would happen. It would just be any other isotope, which is what makes these, I don't want to say special because it's kind of frightening, but yeah, that's what happens. All right, so fill in the missing products, fission reaction. I'll do 4A and I'll leave B for you guys. So we're starting with uranium-235 and then we're bombarding it with a neutron. So this was the breakdown we looked at the very beginning of class. And when uranium splits, it can split into a bunch of different things. It's not always the same stuff. So we have, in this case, yttrium and something else. We need to figure out what it is. So we're going to use a little bit of math to help us figure out exactly what it is. So on this side, we have 235 plus 1. So how many protons and neutrons did we start with? We started with 236. How do I know that? Well, I have to have like math, you know? 235 plus 1 equals, this is 100 over here, so there's 100 plus something plus 1. So over here I have essentially 101. That's 100. Let's go with 101 plus something has to equal 236. So what does that something have to be? Just do some quick mental math. 135 should work. So does 236 equal 100 plus 235 plus 1? 135, I should say. 235. So this is how these all work. You just need to make the math work out. So on the left, I have 236. Done. 100, 135, 1 is going to give us 236. So the blank here is going to, it has to be 135 because that is the only thing that will make this equation work out. Now, the bottom number is the more important one. Well, not necessarily more important, but it's the one that's going to tell us what element we're dealing with. So we have 92 plus 0 is equal to 39 plus something plus 0. So we're going to have 92 is equal to 39 plus something. So if I break out the calculator, still have it up here, I'm going to subtract 39 from 92. I'm going to go 92 minus 39. That's going to give me 53. So the missing blank here is going to be 53. 53 plus 39 gives us 92. So I put in my 53, and I can look to the bottom number to figure out what element I'm dealing with here. So element number 53 on the periodic table, 53, 53, 53. Is that iodine? That is iodine. There we go. So we get yttrium and iodine produced. I don't know if you guys remember when the Fukushima plant melted down in 2011. Basically, when there was a big sort of concern in Japan, and especially North America, as the radioactive cloud drifted towards North America, that you would absorb too much radioactive iodine. And this happens a lot when the nuclear power plants melt down. The radioactive iodine gets released in the atmosphere, gets absorbed into plants and things, and then you eat it. And you have a gland in your neck called your thyroid, and your thyroid absorbs iodine. It needs iodine to work. So what people did just after Fukushima plant reacted and broke down and melted down is they took a bunch of iodine supplements, and there was a shortage of iodine because they wanted to fill up their thyroid with clean iodine. So when the radioactive iodine came, they wouldn't absorb it into their thyroid and get thyroid cancer and all that other fun stuff that comes along with having radioactive stuff in you. So that's a pretty common isotope to be created when uranium falls apart, is that iodine. I will leave the second one for B with you. I'll do 5 though. Let's look at 5. We'll do a few more off the extra practice sheet as well. 5, Eric wanted 13. All right, so same deal here. On the top I have 235 plus 1, so just looking at the top numbers here. Arrow's kind of like an equal sign, 145 plus 88 plus something times 1, or just something. So I need to figure out what this coefficient is going to be in the blank here. It can be a number. It's going to be a 2, 3, 4, 5, 6. So let's do the math over on the left side. 235 plus 1 is going to give me 236. 145 plus 88, let's just calculator that. 145 plus 88. It's going to give me 233. And then I'm going to add something to it. So what does this blank have to be? It's kind of looking like a 3 at this point. 236 equals 233 plus 3. Because if I put in a 3 here, 233 plus 3 is 236. 236 equals 236 on both sides of the equation. So this one's a little bit different because instead of giving you like a missing thing like bromine, it just says how many neutrons are produced. And in this example, we have 3 neutrons being produced. Are we okay with that? 4, 5, 13. That's the next one. Elements heavier than iron cannot form in a star. Instead, they form when stars explode. What is this phenomenon called? Does anybody know what happens or what's called when a star goes boom? You guys study this in grade 9, I believe? Nobody knows what's called when a star goes boom? A supernova. You've probably heard that term before. Thanks, Kaylin. Look at that. Shows up, has the answer right away. Looking good, Kaylin. Looking good. Supernova, yeah, when a star explodes. So stars can make iron. Our star, our sun, as I mentioned a couple days ago, is a really small, tiny little star. It won't ever supernova. It doesn't have enough stuff to supernova. But our star will only make like up to beryllium, I think, maybe a little bit heavier than that. Bigger stars can make bigger elements, and when they go boom, they make even bigger elements, and that is the stuff we're made of, and the stuff like this table and this pen and computers and calculators, all made in stars. For sure, Kyla. Radioactive decay number 14. Is that this guy here? Half-life. Nuclear reactions. Radioactive decay. Sorry. There we go. Let's find the right one. All right, this one's asking kind of what we're starting with here. All right. Again, it's kind of similar to the question I just did. And you need to kind of look at the math on the top. So I have 4 here and 263. And then I have an equal sign and something equals 4 plus 263. So it's going to be probably 267, I would guess. So 4 plus 263 is 267. And then same deal on the bottom. I have 2 here plus 105. So on this side I have 107. And I need to figure out what element that is. And we always look to the bottom number, this is the atomic number, to figure out what element we're dealing with. So element 107 on the periodic table is going to be one of these ones at the bottom. Looks like BH. I can't even read what that is. I'm not familiar with it. So BH gives off an alpha particle. That's 42He is an alpha particle. 2 there. And that is what's going on there. Are you all right with that, Kyla? Is that still unclear? All right. Anything else out of the learning guide that we wanted to look at? I want to also look at a few questions from the extra practice sheet. And there's a bunch of fission-fusion reactions here, so give us a bit more practice. So if there's nothing else from the learning guide, I'll just go do that. All right, so what I'm looking at here is in Unit 7, there's the half-life decay extra practice right here at the top. And I want to go through just a few of these. So it's just a PDF document. And if you didn't do the half-life decay, the half-life activity, then you are going to do this sheet. All right, so the first page is a little 12-question quiz on half-life. Drawing your little half-life tables, dividing by 2, either talking about the mass or percent. Remember, almost all of these questions from like 5 or 6 on, you're always going to want a table that looks like half-life, you could have time, and then you can have an amount. And the amount is going to be either a mass in usually grams or a percent. Could be either one of those. So we start at 0 half-life, 0 time, and 0 amount, and just kind of work from there. Go 1 half-life. How much time did that take? Some questions it's important, some it doesn't matter. If it has it, you can include it. If it doesn't, don't worry about it. But you're always going to need probably some sort of time measurement, whether it's half-life or years, and then you're going to have some sort of mass measurement where it's percent or grams. So that's the first, I think, like 12 questions, just multiple choice. There you go. The second part is the fission and fusion examples. So these are these radioactive sort of decays or induced radioactive decay, things like that. So we've done one really similar to number 1 in the learning guide, so I'll just go right to number 2. And number 2 is a fusion reaction. So H hydrogens, normally hydrogen is just one proton and one electron. That's what hydrogen is. But in this case, we have hydrogen with a neutron, and that's called deuterium. And that's a special isotope of hydrogen, not very common. So I need to do the math. Over here on the right, I have 1 and 3. So together that gives me 4. Over here I have 2 plus something gives me 4. So I know it's a 2 because 2 plus 2 is 4. And over here on the right I had 4. And then on the bottom I have 1 plus something is equal to 1 plus 1. So this is likely going to be a 1 on the bottom because 1 plus 1 equals 1 plus 1. So element number 1 on the periodic table is going to be hydrogen. So this is 2 isotopes of hydrogen, 2 deuterium atoms combined together to give us 1 standard hydrogen, so that's just regular hydrogen, and then hydrogen with 3, a mass of 3 is called tritium, which is another isotope of hydrogen. Let's look at number 3. 3 is a bit tricky. So I have, on the top here, I have 1 plus 235, so I have 236 over here, is equal to 152 plus something, not sure what that is, and then I have 4 times 1, or 4. So 236, this is what I'm going to work with. 236 is equal to 152 and 4 is going to give me 156 plus something. So if you want to use your calculator, you can just go 236 minus 156, and you end up with the blank being 80. So 80 on the top, and then we do the same thing on the bottom. I have 0 plus 92, so I have 92 is equal to, I have 60 here, so 60 plus something, what I'm trying to find, plus 4 times 0, it's going to give me 0. So that should be hopefully 32, because 60 plus 32 is going to give us 92 plus 0, so that should work out. I need to figure out what element I'm dealing with, and I always look to the bottom, and element number 32 is, oh, wrong screen. We can get it, we can get it. Oh, there it is. It looks like germanium, Ge. So I put in Ge for germanium. Any other ones you want me to do specifically on this sheet, or I'll do a couple more. Is that 10 for me, Kyla? Last one. Okay. Let's do number 10 at the very bottom. So this is something's being bombarded with a neutron, and the neutron is causing it to break down into Te and Mo. And once we get into these big heavy elements, I'm not so good with the symbols anymore, but I think it's beryllium and molybdenum perhaps. 3 additional neutrons are produced, so this is would be a good candidate for something to undergo fission. All right, I'm trying to figure out what element I'm dealing with here, and its mass, and I don't really know what it is, so I need to kind of do some math, figure it out. So on my right side, I have 137 plus 100 plus, and then 3 neutrons is going to be 3 times 1, or 3. So 137 plus 100 is going to be 237 plus 3 is 240. All right. So on my right side I have 240. On my left side I have 1 from here plus something. So that something should be probably 239. Because 1 plus 239 is going to be 240, and that is equal to 240. So my sides equal out. All right, so that's the top. Let's deal with the bottom now. Over here I have 52, I have 42, and I have 3 times 0, which is just 0. 52 and 42 together give me 94. And then on my left side I have 0 plus something is 94. So that something has to be 94. Element 94, it's going to be very bottom line there. That's plutonium. And plutonium is really radioactive, and it's really good at making bombs, but it's not a naturally occurring element, so we have to synthetically make plutonium. And this is one of the problems with in Iran right now. They have nuclear reactors, and they use it to produce energy. They use these nuclear reactors to produce medical isotopes. So if you need, well, I was in a car accident a long time ago, and I went to the hospital to get a bone scan, and they injected me with radioactive barium. I believe it was barium. And the radioactive barium got absorbed by my bones, and then they put me in a big machine that made lots of fancy noises, and they did a bone scan to make sure all my bones were okay. So that radioactive barium came from probably somewhere in Ontario where they make medical isotopes. So you're in Iran, they're like, we're peaceful, we want, to pursue our nuclear technology to make energy and produce medical isotopes. The problem is that plutonium-239 is a byproduct of a nuclear reactor. So if you are, making energy in a nuclear reactor, some of the byproducts, if you kind of filter them out using centrifuges and things like that, are plutonium. So essentially by running a nuclear reactor for long enough, you can create enough plutonium to make nuclear weapons. And the world I say as North America and Europe, is concerned that countries like Iran are running these nuclear reactors to create plutonium instead of these medical isotopes and things like that. So that is another problem we run into. Byproducts of nuclear reactors tend to be nasty things to make bombs with, which is a problem. Not only are we concerned about Iran having the technology to make this sort of stuff, which they do, we're concerned about other countries' ability to give radioactive materials to people that would, like to blow us up, cause like terrorists and whatnot, get their hands on some nuclear material. That would be bad news. All right, anything else on there that you'd like me to do? Any questions, even from the multiple choice stuff up above? I'm here for as long as you guys have questions. If you guys don't have questions, then we will say sayonara, and we'll call her a day. Anything in general out of Unit 7? This will be our last opportunity to look at stuff from Unit 7. It can be alpha, beta, gamma. It can be fission, fusion. It can be half-life. Any of the big topics we talked about, I'd be happy to go through anything from the learning guide or anything from this sheet and see if we can figure it out. If not, your Unit 7 learning guide should be done hopefully by the, is that from the learning guide, Eric, page 8? Your Unit 7 learning guide should be done hopefully today, maybe by the end of the weekend. And you should have your Unit 7 test written by the beginning of next week, because the physics unit is going to go like that. Chapters 8 and 9, going to fly by. Uh, 7, 8, number 12. Carbon is the most common element found in life. All carbon was initially created in the core of a star. Please write out the fusion reaction where beryllium-8 fuses with helium-4 to create carbon-12. That's a great question. I'm glad you asked that one, Eric. All right, so we're going to have a reaction where we have two things fusing together to produce carbon-12. So there we go. Here we go. It tells us that we have beryllium-8 fuses with helium-4. So beryllium-8 is going to be Be with an 8 up here, and then helium is going to be helium with a 4 up here. Now I know that helium is element number 2. I believe that beryllium is element number 3. If we look at the periodic table here, beryllium's 4. I forgot lithium. All right, so I'm going to get rid of that. How do I know? Well, beryllium Be is always going to be 4. That's the 4th element on the periodic table. Helium is always going to be 2. It's the 2nd element on the periodic table. I also know that I'm producing carbon-12, and carbon with a mass of 12, carbon is element 6 on the periodic table. So I look up, find carbon, top right or top left corner, it's number 6. So is there anything else involved here? I should check my math to make sure no neutrons or protons have kind of been left out. And if we look at the top line, 8 plus 4 is 12, and the bottom line, 4 plus 2 gives me 6. So I don't have to add anything to this. There's no additional protons, neutrons. On the top, 8 plus 4 is equal to 12, and on the bottom, 4 plus 2 is equal to 6. Everything works out in terms of the math. So that's it, the equation. That's all I have to do. There's nothing fancy going on, no extra protons flying out or neutrons or anything like that. And this is obviously an important fusion process that happens in stars because we are made of carbon. And without this exact reaction occurring, we wouldn't be here, which wouldn't be good because I like being here. So there you go. Some stars are big enough to fuse beryllium with helium. Anything else from the learning guide, from the extra practice sheet, from the worksheet activity with the little simulation, the half-life stuff where you're drawing curves and finding out the ages of stuff? Anything at all? If you are thinking for a second, there's this one website that I always like to look at. It's kind of interesting, I find. It's called NukeMap. And Alex made this sort of nuclear bomb detonation simulation. So you can put it in any city you want. Of course, we can put in Kelowna. So what would it look like if a nuclear bomb were detonated in Kelowna? For some reason, somebody wanted to, harm us in Kelowna. And this gives you a bit of an idea of sort of the sizes of the nuclear bomb. So we just watched at the beginning of class how many nuclear bombs were detonated on Earth, up over 2,000. And you kind of wonder, like, well, how big or how devastating is a nuclear bomb? So we're going to center this bomb over Kelowna. I can pick whatever bomb size I want. And what I'll do is, let's pick a 10 kiloton one. And 10 kilotons would be the one that the North Koreans would have tested in 2013. So we know that their bomb would have been about this big. So a kiloton is 1,000 tons of TNT. So 10 kilotons. So their nuclear bomb, the 2013 test, would have been about 10,000 tons of TNT. Imagine how big a ton of TNT is. So the yellow circle on the inside, that's a fireball, so everything would have been incinerated. The green one would be radiation dose. Anyone inside the green circle would likely die of radiation poisoning. And then everything inside the outer circle, that grayish brownish one, would cause almost all buildings to be knocked down. So that would be most of downtown Kelowna gone. And that's a really, really small bomb. Let's go to a bigger bomb. Let's go to the first bomb dropped on Hiroshima, a little bit bigger. So the gray circle is an air blast of 5 psi, so that would be enough to knock down most buildings. Anyone inside of the orange circle, the outer circle, would have got a 3rd-degree burn. And a 3rd-degree burn means that you don't even feel it because it goes all the way through your skin, and it basically kills all of your nerve endings. So it'd be like the worst sunburn ever that you wouldn't feel because you've just killed all of your skin. That would be if you're exposed. So we're looking at, from Knox Mountain down to just past the hospital. All the buildings inside that little circle would be gone, essentially, knocked over. So that's a small bomb. That's the first bomb. The Nagasaki bomb was a 20 kiloton one. It's a little bit smaller. Let's go to something a bit bigger. Anyone heard of the Cuban Missile Crisis? That was a pretty scary time in history. Mr. Ross lived through it. So the Cuban Missile Crisis, the USSR, Soviet Union, tried to ship a nuclear bomb to Cuba. And that is a 2.4 megaton, so that's 2.4 million tons of TNT. Essentially, the fireball would burn most of Kelowna. The shock wave, the gray circle, would have knocked down every building from McKinley Landing down to the southernmost part of Kelowna. Most of downtown would be vaporized instantly. All the buildings in Kelowna would be knocked down. And that is still a small bomb, believe it or not. Let's go to something big. The largest bomb ever, let's go to the largest US bomb, 15 million tons of TNT. Again, the circle doesn't really mean much at this point because it's just so darn big. But 3rd-degree burns out from Kelowna all the way to, well, this is Big White right here in the bottom right corner. There's Big White. So almost all the way to Big White, 3rd-degree burns. Let's go to the biggest bomb ever detonated. The Soviets had a 50 megaton bomb that was designed as a 100 megaton bomb, so that's 50 million tons of TNT equivalent. And we're talking Vernon to essentially Penticton. Everything in there, all the people would have probably died. Air blast radius, pretty big. And they designed it to actually be a 100 megaton bomb, so twice as big, but they thought, this might be a bad idea, let's just leave it at 50 for now. And that's what a 100 megaton bomb would look like in terms of radiation, the air blast. Just to give you a bit of perspective on that, if you've ever been to Vancouver, you know how big Vancouver is. So let's move that bomb to Vancouver and see what happens. Most of downtown, or all of downtown, would be incinerated in the fireball. The air blast would knock down houses from all the way over, we could move it, I guess, to kind of maximize destruction here. From Vancouver all the way to Abbotsford. Kaylin, are you in Abbotsford? You might be okay. Just get some bad sunburn. The actual, 3rd-degree burn radius would go in everything from Chilliwack all the way to Vancouver Island. All in one go. So that is what a big bomb would do if detonated in a major city, essentially killing millions of people instantly, vaporizing them. There you go. So that's why nuclear bombs are scary, and we hope that we never have to deal with them in terms of war ever, because you can literally, by pressing, I'd imagine, a series of buttons, kill millions of people, knock down entire cities worth of millions of people's houses, and give radiation dose to and burn people up literally hundreds of kilometers away from the actual detonation. So there you go. That gives you an idea of how scary nuclear weapons are if you didn't think they were scary enough. If nobody has any additional questions, we'll just leave you there for today. And I don't see anyone with additional questions. So next day we're going to start Unit 8 on Tuesday. Unit 8 is the physics unit. We'll go through it real quick because it's not terribly difficult. It kind of looks a little bit like math, really basic math, multiplying, using formulas and things. And the equations that we're going to use are on the back of your data book. So if you have a data book for next class, that would be handy. It would be super duper great if you could finish off this Unit 7 stuff before next class, because you don't want to be kind of plugging away through chemistry and then Unit 7. Unit 7 kind of just stands by itself. You don't want to have to worry about that stuff when you're doing the physics unit, because you're trying to fight the battle on two fronts. So it'd be awesome if you guys get caught up, and then we just have the last two physics units left at the end of the course. Then we can do some review, and we're done. Done. I'll leave you guys there. We are climbing tomorrow at 11 at nice gym, just kind of behind Costco area. It was really great last week or 2 weeks ago. We had a ton of students show up and it was good. There's lots of places to climb, so there's lots of room, and you don't have to be experienced. They give you shoes, you just go climb up a wall, and it was great. So hopefully see a couple of you guys there. And if not, we'll see you in class again on Tuesday next week with your Unit 7 done. Please be done your Unit 7 next week. Thanks. Have a great afternoon. Enjoy the weather, and we'll see you on Tuesday.